Welcome to my talk. Today I'm going to present Telepath. It's a framework on sensory offloading for wearable devices. This work was done with my lab mate Choing and my advisor Ben at Duke. So the scope of our work is to aggregate resources from multiple mobile wearable devices that are often carried simultaneously by today's users. And in specific, in this paper, we focus on the continuous sensing wearable applications and how aggregated resources can help with activity tracking. If we look at today's wearable devices, we see two clear trends. One is that they are equipped with system on chips that are more and more powerful, so they are computationally competitive with phones. On the other hand, they're extremely short of battery capacity. So on average, a smartwatch has about 11% of a phone's battery capacity. And what does this mean? It means that although there are already a lot of continuous sensing applications on the wearable market, and the wearable devices are capable of running them, but they might not be able to run long enough. So a lot of these apps will drain the wearable's battery in a few of hours. And the problem is the high sensing cost. Let's first look at an example app. And it has a typical architecture of a continuous sensing app. It has 3 modules. Sensing is to collect raw motion signals from sensors such as accelerometers and gyroscope. Feature extraction is to compute features such as standard deviation or how much energy this signal contains. And then classification is to identify what the user is doing, what activity the user is doing, based on the value of the features. And if we look at such an app, we see 2 sources of energy consumption. One is from sensing, one is from computing. And we notice that the cost of sensing itself is a significant part of the whole power consumption of the app. And if the app just simply calls the sensor API to listen to events from the accelerometer, it will consume about 200 milliwatts of power. And the reason is that the CPU has to be awake for the data movement to move data from the sensor to system on chip. And due to the large amount of data, the cost of sensing cannot be mitigated by traditional computational offloading schemes. So, of course, one solution is to improve the hardware of wearable devices. For example, we already have accelerators that identify certain activities with certain algorithms and bake into hardware. And this is energy efficient because now the data directly move from sensor to accelerator. And so the main CPU can sleep. And it's fast because the algorithms are now baked into hardware. However, it is not a scalable solution. It's limited to a few activities and a few algorithms. And if we want to improve it, we have to go through a very long development cycle. We need engineers to do simulation, ASIC design, verification, all the way till tape out. And as an app developer, I do not want to wait that long for my app to be able to run on wearable devices or to be able to have a good usage of these devices. So I want an ideal solution that is not only energy efficient and fast, but also scalable for any sensing app. And it's, of course, easy to deploy just as an Android sensor app. I want this new solution easy to use for app developers and easy for existing apps to migrate to. So for developers who already have wearable sensing apps on the market, they need a solution that they can quickly adapt to. So we propose offloading sensing and computing all together. And our observation is that since today's users often carry multiple devices, smartwatch, phones, tablets, and we noticed that if they're carrying multiple devices simultaneously, there is a strong correlation in the motion signals of multiple devices. And here's an example. When a user is wearing a watch on her left wrist and a phone in her right pocket and she's walking, we see a strong correlation in the x-axis acceleration of the 2 devices. And so we wonder if we can take advantage of this correlation. Can we just use the phone to take over the watch's sensing and also computing all together? And that's what we call sensory offloading. So the idea is simple. It's basically let the phone emulate the watch for certain type of tasks. it has two steps. First is to let the phone predict what the watch is sensing. So if the motion signals on the watch looks like something on the left figure, we want to predict it from the signals on the phone, what something look like on the right figure. So we want to build the connection and make the prediction so the phone knows what the signals look like on the watch. And after that, we can just let the phone do the computation. So here's another point that I want to emphasize, which is activity recognition applications often have a carefully calibrated model to recognize activities. For example, it might be a support vector machine to identify whether the user is running or walking based on some feature value. And to build such an app and to build such a classifier, developers take a lot of effort in collecting data and do user study and calibration. And if the phone can know what the watch is sensing, then it can emulate everything. So the developer do not have to build another model for the phone. They just can clone it, and the phone can emulate the watch directly. So this is the second step. So as a developer, I think this is a scalable solution, because for developers who already have applications on the market, they don't need to redo everything from building the classifier. They can just clone whatever that's already running for the wearable device to the phone, and now they can have a solution that runs across platforms. So to design a framework that supports this type of idea, we have several considerations. The first is, of course, we want to make sure that it is actually workable. The phone can predict what the watch is sensing, and it must be energy efficient. We do not want some complicated data processing that make the phone dead while let the watch alive. Of course, it have to be easy to use, and also it should be fault tolerant. It should handle various device placements. In this paper, however, focus on the first 2 points. We want to build a prototype that demonstrates this is a workable idea. So we designed Telepath as a shim layer that sits on top of a mobile OS. For example, an Android app, instead of talking to Sensing Manager API in Android, it now talks to Telepath Sensor APIs. And the Telepath layer will handle remote or local data streams. The workflow of the Telepath framework has 2 execution modes. One is the local mode, one is the remote mode, the offload mode. The local mode is basically exactly the same of what's already there on the wearable device, from sensing to computing to display it on the user interface or log it in some database. But then on the other hand, the remote execution, most of the things are done on the phone. So from sensing, the phone collects sensing data locally, and then it will go through a predictor mode that tries to predict what the watch is sensing. And the predicted data will be used in a cloned app, the cloned computation. Exactly what is running in the wearable device is now running on the phone. And then the final result, such as the activity label, will be sent over Bluetooth to the wearable device. And an important module is the verification module. It periodically collects raw sensing data from both devices to verify if the correlation is strong or not. If not, it will terminate any ongoing offloading process. And of course, we can tune the frequency of verification for the trade-off between energy and accuracy. But we think the technical challenge in this framework is how to build a predictor. After experimenting with many algorithms in time series analysis, we settled with a 2-step pipeline. So from the raw sensing signals of the phone, we first enter a clustering module and then enter a transfer function module, and then we can get the predicted sensing data of the wearable device. And I will explain them one after another. Let's first look at transfer function. Transfer function is a technique used in time series analysis that captures the relationship between 2 strongly correlated time series. So this is a transfer function. The output is something we want to estimate. So in our case, it's the watch's sensing data. The input is the phone's sensing data and the history of it. And then transfer function modeling is the process of learning this function. To learn this function, we want to know the noise series, what this captures all the other effects in this relationship. And we want to know the coefficients of this transfer function. So this means that we need to first collect some data offline from both devices to build such a correlation. However, we notice that we cannot just easily build this. And there is some constraint in the real use case of mobile devices. And I will explain why. That's why we need the clustering step in the first step. So the reason is that is something called data stationary. Data stationarity is something in time series that means the statistical properties of time series do not change over time, such as mean variance and autocorrelation. And this consistency makes the time series easy to predict. And we notice that if the data do not have stationarity, if you build a transfer function model out of it, this model won't be accurate. And say if we just collect data from both devices of day long, we cannot just build one single model out of it because users perform different actions. And so the correlation relationship between multiple devices, they're also changing over time. So that means the data is not stationary. On the other hand, we also notice that within each individual activity, for example, when the user is running, the motion signals appear to be stationary. So this gives us the idea of first doing a data clustering for the training data. And then for each small cluster, we will generate a transfer function model out of it. So we call this a hierarchical transfer function modeling. And at the real time, when new data come in, we will first try to identify which cluster it should belong to. It doesn't have to be a semantic cluster. It's just something similar to previously trained data. And then we will fetch the corresponding transfer function and then get the predicted data. So overall, we have the following training pipeline. We will collect data with some logger from both devices when there is ample amount of power, and then offload to some remote server for pre-process when the devices are being charged. And this pre-process includes the denoising, interpolation, and identifying whether the correlation is strong, etc. And afterwards, we'll enter the clustering phase. For each cluster, one transfer function will be computed. And the computed transfer functions will be downloaded to the phone to work real time. And notice that this is a repetitive process that can be executed daily so that we can keep up to the changes in the device usages and the correlation relationship between devices. To evaluate Telepath, we use a simple baseline. Basically, we want to know if we directly use the phone to run everything, to run watches code, how much accuracy we can get. Does that work? And that's our baseline. So we want to measure the accuracy of identified activities and also how much power is being used by each device. And for the applications, we want to build a target app that identifies some example activities. And we surveyed top 14 wearable apps on the market that are for continuous sensing. And we noticed that they are trying to classify whether the user is running or cycling or walking. So we use these as our target activities. And our metric is F1 score. The y-axis is F1 score. It's an aggregated metric that measures the accuracy of activity recognition. So it basically combines precision and recall. And it ranges from 0 to 1. The higher the score, the better the accuracy. And on the x-axis, we basically use a spectrum of classifiers and to see whether the phone can actually identify the activities with classifiers that are trained originally for watch or for wearable devices. So without Telepath, if we're directly using the phone, basically it is not possible to identify the correct activities because after all, the data streams on the two devices are different. With Telepath, however, we are able to achieve 85% of the accuracy of what the watch does. So in other words, by shifting sensing and computing from watch to the phone, we are losing about 15% of the accuracy. Is this a good result or not? Well, we are losing some accuracy, but what do we gain out of it? We gain battery life. So potentially Telepath can extend the watch's battery life by 2.1x. Here is a figure. On the leftmost bar, we show if everything is running locally, exactly what we already have now, what is the remaining battery life. So that's about 5 hours. And then Telepath is able to double it. We also compare two other baselines. One is to completely offloading the computational part. So sending raw sensing data over to the phone, of course, is not going to work. And then another scheme is to send extracted features to the phone. And neither of them is able to improve the battery life. So in this sense, Telepath outperforms traditional computational offloading schemes. While doubling the battery life of the watch, the phone's battery life decreases significantly. And so here we are seeing a behavior called transfer of battery life. Although I have to point out, we were not using a very energy efficient phone. It was a quite old phone. But nevertheless, the phone has to sacrifice some amount of battery life. But we think still the remaining battery life on the phone is still larger than the remaining battery life of the wearable device. So we think the aggregated battery life of multiple devices has been improved. And this means that if we can shift some tasks from the watch to the phone with negligible performance loss, then we can leave the watch or the wearable devices to do something that only these devices can do, such as gesture recognition. So this framework is not trying to get rid of the watch, but instead is trying to offload something that is offloadable and then give the wearable devices a better usage of its computing power. So in conclusion, in this work, we attempt to make a collaboration between multiple devices, and we experiment on continuous sensing applications for activity tracking. And we demonstrated with signal processing algorithms, we're able to sacrifice 15% of accuracy loss for a 2x battery life improvement. So the future work of this paper, it can be another application of such a collaboration among devices, or it can be better algorithm for data processing or better management policies, such as when to offload, when not to maximize the energy gain and minimize the performance loss. That's it. Thank you very much. I welcome any questions.